careful how you do things. Data structures and compiling and so forth like that.
Special cases seem to, maybe it's just the way I tend to
well,
understand it.
That's in the philosophy of how you understand any problem. When you first go to a problem, it seems like a whole bunch of totally disconnected special cases which don't bear any relationship to each other. So you have this giant program which treats any special case. And as you study the problem, you discover common elements, and you're able to merge the code together so that you get something that handles all special cases.
If you're 90 degrees away from Jupiter, everything goes to hell.
Yeah.
And that seems very strange, If you look at a cube, even if you're close to the cube, it's all right.
Yeah, I don't know. Well, let's see. We were in the process of talking about scanline algorithms for polygons, or for patches. So we talked about two techniques so far. One is the Catmull technique of recursive subdivision. You just keep splitting it into smaller and smaller pieces until you get one that's a pixel size. Then started in on talking about the more mathematical iterative approach, which is the generalization of polygon tiling. And just kind of got into that. Basically the idea is here, you're going to pass a scan plane through this thing from top to bottom. And so as a scan line or scan plane goes down the screen, you're keeping a list of active patches, just the same as way you would with active polygons. You tell it when a patch becomes active because it passes between a local maximum of the patch. There are three types of local maxima we're interested in. Real ones, where the thing really bulges up and the corners of the patch are down here. Ones which happen only by virtue of an edge on the screen here. And ones which are really a corner sticking up. This last one is the ones that only shows up with polygons, but the other two can't show up with curved surfaces because the edges are no longer straight and the middle of the thing is no longer straight. Now, how do we find these things? When we start getting into these sorts of algorithms, you wind up using numerical analysis a lot and a lot of heuristic sort of techniques. It's a little bit sloppy in that sense, but it's maybe a little bit more mathematically complete. There are a whole lot of algorithms for doing this thing, but basically the idea is you start out with some initial guess, and then you move that initial guess in the direction that causes the y-coordinate of this thing to be higher than it used to be. And this is called hill climbing. Whatnot. All of these things generally wind up taking their initial guesses and they evaluate the derivatives and maybe the second derivatives of the patch at this point, and then locally approximate it by a simpler function. If you just have the function and its two derivatives, you can locally approximate it by a plane and know which direction is going upwards on the plane. If you use the second derivatives, you can locally approximate it by a second order surface, say paraboloid or ellipsoid, something like that, and go up. And basically, you climb up the hill until you get to a point where all directions are go down from there. Now, these local maxima of this sort are the mathematical local maxima, and they are characterized by having the two partial derivatives of the y function equal to 0 here. Partial of y with respect to u and partial of y with respect to v. I'm using u and v as the two parameter values here. Sometimes they're called s and t, sometimes they're called u and v, but the names don't matter. And so, in a sense, this is another sort of bivariate Newton iteration thing that you're doing here, and that you have some function equals 0, some other function equals 0. You're trying to find the points on the patch where both of those functions equal 0. And so you can use that same formula that I referred to last week to do that. Now, in the process of doing this hill climbing, you keep nudging this point, and each time you nudge the point a little bit, you have to test to see if it's nudged it off the edge of the patch, which is, the u equals 0 and v, and 1 and v equals 0 and 1 boundaries. And this is what would happen if you had this sort of a local maximum. Start with an initial guess, and it's going to drive you up in this direction like that. So it's going to, the real mathematical local maximum of this thing extended out to infinity is up here someplace. But if you have to cross over the boundary, then that means that the local maximum is at the edge of the patch. And so then you kind of block onto the boundary and you just crawl along this to find the maximum of the thing. And if that drags you across a corner, then you know that the local maximum is at a corner of the patch. So what you can do is just start out with 4 initial guesses at the 4 corners and maybe the middle of the patch, and drive those each in the direction of the thing in case the patch has more than one local maximum. It's possible to have a patch like that, so that when the plane passes this local maximum, you have to start creating sample spans here. When it passes that local maximum, you have to start creating sample spans there.
Well, you have any number of crossings of the scan line?
In the general case, if you have an arbitrarily defined functional patch, you can have any number of local maxima. In the case of bicubic patches, since they're cubic polynomials, the cubic polynomial can only have just one equation, can only have effectively 2 local maxima if you limit it at the boundaries. A bicubic patch is more like really a 6th order function, because there's the u cubed and t cubed terms in there, which is a 6th order term. And so you can have, I think, something like 4 or 5 possible local maxima. Imagine the bulges and bumps in there. So you have to keep a list of these things. In a sense, it's like, having several different polygons. They each have their own local maxima. Here you have one patch with several, that's all. Now when a patch enters and you go down the top here, you have to set up some kind of set of data blocks for the edges that you're going to keep track of. And so you keep track of the points that are either along the edge of the patch itself, where that intersects the current scan line. And so they're all defined by something like this: y of u comma 0 equals 0, or y of u comma 1 equals 0, depending on which edge you're on. So this is essentially a univariate function of u. And so you can use single varied Newton iteration in order to keep track of where this thing goes from one scan line to the next. For places where the patch bulges, what you're doing is taking a slice off, like a slice off the top of an egg here, and so the 2 edges on this thing are not edges of the patch necessarily. They are instead silhouette edges of the curve. And so these are the places where the z component of the normal vector is 0. Which is defined mathematically by the cross product of the u and v partial derivatives of this function. Yeah.
What's the difference between these 2 again?
The difference between these 2?
Yeah.
In the top one, it's the it's kind of a funny diagram, isn't it? It's the actual edge of the boundaries of the patch here that's intersecting the scan line. And in the bottom one, the boundaries of the patch are maybe back here someplace. It's the inside of the patch that's bulging up, poking through the scan plane. And so you have these 2, well, these 2 equations here, both having to be solved for 0, and so you have to use bivariate Newton iteration for these things. It involves taking the derivative of this and so forth, so you wind up needing to calculate the second derivatives of the u and v function in order to be able to keep track of these boundary edge trackers here. And as you might expect, we're getting into a fairly noticeable amount of arithmetic here. But these things are polynomial functions, which are about the easiest things to take derivatives of. And in fact, you can kind of pre-calculate a lot of the coefficients, even if you've got enough space to hold all matrices. And so you track along all these things until they hit a local minimum, at which point they disappear. So for a particular scan line, then you have these lists of edges which are the endpoints of sample spans in the x direction. And so there are several patches here Let me get a somewhat bigger diagram. The x loop of this thing, the inner loop, looks sort of like the y loop, only, again, the dimension is reduced by 1. For a particular edge like this, we kind of pass the thing through and we have a list of entering and exiting edges in the X scan, and those are triggered by when you pass the endpoints of the thing. So that when the thing enters within this particular edge, we have these two equations we have to satisfy. Again, 2 equations and 2 unknowns, and we solve that iteratively by variant iteration to crawl along this thing, and this will track the u and the v as it goes along the thing. Then for a particular pixel, once you've got u and v, you just plug that into the z equation. That gets you the depth, so you have the thing to compare with all the other patches there to see which is in front. Yeah.
Question, what if the second bump comes in front of a higher hill behind it?
How does this look now?
Well, just sort of like...
Let me try. Yeah, a bump here.
Okay, so there's a bump, and then there's another bump in front of it.
And there's a bump here, like that.
No, well, that's one particular case.
Yeah.
That's one particular case, but
Yeah.
I was thinking specifically the case where the second bump is below the first bump, but it's still in front of it.
Like that?
But no, you just have one bump there. Draw a little
here's the bump.
curve,
Okay.
just under that curve.
Like that.
That's right.
Okay.
That's all one patch.
Okay. In each case, this is a local maximum and that's a local maximum, right? And so they appear 2 places in the data structure, and so for a scan line that comes in here, this one will have entered, and it's got its edge tracking things created, and so it's in the X thing. As this thing works down here, you've still got the X edge like that, and then this one is entered, and so it's got another X edge. You can sort of think of this thing as dynamically slicing the patch up into a bunch of 1 pixel high polygons almost, or polygon strips. And as you go along, you trace along the curve in the X direction rather than doing a straight line interpolation between it. Now, this particular thing, as you might imagine, is sort of slow, and especially it's the X loop that you've got to worry about, because as you crawl along each pixel here, you've got this bivariate Newton iteration to keep track of exactly where the thing is. Now, there are a couple things you can do to speed this up. One is, in terms of all these iterative schemes, you can speed them up by making some somewhat more intelligent initial guesses at what's going on. If you imagine let's see here. Just imagine the single variable case. This is the y value along one edge. We're just plotting as a function of the parameter value. And so the parameter goes from 0 to 1, and so this is the y function of an edge. And as the y scan lines go down like that, we're going to keep track of the intersection of this function with the 2 scan lines. Once you've found one of these things for one scan line, and once you've found one for the next scan line, the Newton iteration generally would use the current position as the initial guess for the next position for the next scan line. But you can be a little bit smarter than that by saying, well, the previous scan line was here, and on this scan line it was there, so let's kind of extrapolate this down by 1 pixel, one scan line distance in order to make an initial guess for the Newton iteration that's down here instead of up here. This is going to be a lot closer to what the real answer is. And in fact, for the pictures that I did some experiments and discovered that the kind of average number of iterations that it takes to converge is less than 1, because most of the time this initial guess is going to be close enough, so it satisfies the criterion of convergence without even ever doing the iterative step, which is subtracting off y over y prime. And so you can fairly intelligently track these things along, especially when they're sort of flattish looking, then they're kind of automatically treated as being pretty much linear. Similar things for the bivariate case, in which case you've got a u and a v direction that you're keeping track of, and you just extrapolate the previous u and v values, the current u and v values, you go the same distance in parameter space for the initial guess on that. But the other thing that was done in order to speed this thing up is to take the inner loop, the x portion of this thing, and instead of doing a whole iterative thing to track along the exact position of the curve, we're breaking the curve up into a whole bunch of little straight line segments. And so this is even more like chopping the thing up into polygons. If you look at a top view of this thing, just as the bulge in one of these things pokes through the y-scan plane, the intersection in the xz space is doing some circular shaped thing. And what we're doing is we're dividing it now into two pieces, where the z normals are zero, those are the two endpoints. And we're kind of iteratively tracking along this thing as we scan along an x. Rather than do that, let's instead make a whole bunch of other pieces here that are defined in a way to be mentioned shortly, and track those things as they go down from one skyline to the next, and just connect these together with straight line segments. And this will give you a fairly good approximation of the thing, kind of dynamically created to fill in this thing with straight line approximations. You can do Gaussian shading in between this thing and get a fairly smooth result. Now, how do we define these things? And so think of the normal vector of this thing as we look down from the top. These two we've already defined as being where the z component of the normal vector is equal to 0. We can define these two as where the x component of the normal vector equals 0. That is, the plane is exactly facing us. And we can define this one as the x and the z component of the normal vector are the same but of opposite signs. It's a 45-degree direction. And here where they're both equal to each other, and so forth. And so all these other sample points are going to be defined in terms of the direction of the x and z component anyway, the direction of the normal vector. And they'll be equally spaced around a circle. So, let's take a look at what this is going to do to certain types of shapes. For a circle, for example, it's going to break an exactly circular section up into, in this case, 8 equally spaced straight line segments, which is pretty much the optimal way. They're equally spaced around here, and so the straight line approximation to it matches the circle pretty well. If you imagine kind of a long, skinny ellipse, it's going to break it up into here, and here, and here, and here, and then this 45-degree tangent line is going to be like about there, and this one's going to be about there, and this one's going to be about there, and this one's going to be about there. And so we've broken it up again into 8 straight line segments. But this tends to cluster the little samples of this thing in places of large curvature, which is what you want, right? This is kind of the best way to divide this thing up into straight line segments. And so instead of just tracking the z normals, the silhouette outline as you go down, you also track the x normals and the x plus z normals, and you can have any number of equally spaced kind of prongs sticking out of this thing. I think I used 16 in the actual program, and have a fairly good polygonal tiling of the cross-section of this thing as it goes down. Now what this means is that the data structure for keeping track of these things is a little more elaborate, because you have to keep track of not only where these things are, but the connectivity of them, which is fairly simple to do. It's just a forward-length list of points defines the contour curve in the intersection plane. But funny things can happen to this thing between one scan line and the next. To look at a saddle point, for example, and if you imagine the scan plane going through like that, looking down on the top of this thing, you're going to have an intersection looking like this, and it's going to have a sample point here, and one here, and one here, and one here, and one here. They're going to be linked together. ones that actually hit the edges are also explicitly in there. So you've got this list of points starting at an edge, a bunch of internal points, and then winding up at an edge for each of these things. The next iteration down, this thing might move over here, this thing might move over here, this thing might move down here, and this thing might move down like that. But if the thing drops below the local point in the saddle point here, then certain of these things are going to disappear. This one and this one are going to fail to converge because they're tracking on this point like here, and that doesn't intersect this line here. So your Newton iteration both has to be able to detect that and recover from it gracefully. And it also has to realize that when these two things get broken, they have to be reconnected together. In that suddenly we've got a new sample point popping out here. The x normal is equal to 0, the z is normal, the null is pointing directly towards us here. So we've got to be smart enough to create a new normal here and reglue these things back together. And the technique to do that is sort of described in my thesis, actually. It's not extremely elegant, but it sort of works. On occasion, it requires noticing when these things disappear, and then starting at this point and iteratively tracing along this level curve, it's called, and picking up new sample points until you bump into one that's already there, which point you've gathered them together. Well, how do you detect when you bump into one that's already there? You kind of have to scan through and say, are we real close to this? Do they have all the same normal vector properties and so forth? And if so, then you assume they're the same. Sometimes this will get confused and things go round and round and round, just generating 4 or 5 versions of this particular scan line over and over again. It's a bit messy. So this thing starts out sounding good, but the implementation of it gets a bit messy. But once I got my thesis and got out, I put that on the shelf and didn't worry about it anymore. I think this can probably be enhanced a little bit, but that's something for my retirement or something. Well, what's the next algorithm? The next technique that came along was due to Rain and Carpenter. Actually, before I get to there, I ought to mention another variant of this thing. I ran into a guy named Turner Woodard at a graphics conference in '77 or something like that, who it turned out was doing something very similar to this, only in a slightly different fashion. And it was a bit faster in some respects, but a bit less accurate in other respects. So we give a brief idea of what that is. Let's take an example patch here. Here's the scan line that goes through it. He is tracking along the edges in the same way. The edge intersects the scan plane, and it's got a Newton iteration to go down here. But he's tracking along the the silhouette edges by sort of an approximation technique. Rather than calculating Zn equals 0 at each scan line, he figures out where it shows up and where it leaves, and he calculates the slope of this line here and the slope of that line in screen space, and fits a Hermite curve to it. Pardon me? Hermite curve, this is one of the 5 different types of things that I mentioned before. Hermite means that you're given the endpoints, you're given the slope at the endpoints, and so you come up with a cubic equation which satisfies those 4 constraints. And so you can calculate the slope of this line by finding the tangent plane to the thing and find out what that looks like in screen space. The slope of this line, finding the tangent plane, and so forth. And so you're generating a curve which approximates where this edge is going to be on the screen. It's not going to be exactly right, but it's a lot simpler to solve this one more or less univariate problem as you go down here for this Hermite curve than it is to do bivariate iteration on the 2 real conditions that go on. And then once he's got these 2 things, then he just starts falling shading between the silhouette edge and the object here, which is the edge of the patch. And so it's going to swing the normal around appropriately and do shading like that. So he's not doing an X iteration at each point either. So these 2 things tend to make the thing not quite as accurate, but it's somewhat faster. This particular technique and the faster X-loop technique that I talked about over here do have one disadvantage in that they tend to do mysterious things when objects intersect each other. If you have patch that looks sort of like that, say, and you draw a picture of it using either the wooded technique or this fast X-loop technique, it'll look real nice. If you draw a picture of it with a plane passing through it like this, we actually have to calculate the curve intersection of the object with the plane. Then you're going to get all these little straight line segments in here, which kind of give away the show, in that really this thing's made of a bunch of straight line approximations to this curve thing. When they intersect with the plane, you see them. This won't happen if you actually use binomial iteration for each pixel along here and calculate where the z really is. This is only going to happen when you approximate the z by a whole bunch of straight line segments. So it's always trade-off. You can make better images, correct images with more computation time, or you can make maybe not quite as correct images, but do it a lot faster. One other thing about both of these is that these do perspective correctly. Catmull's patch splitting algorithm didn't do perspective quite correctly. He did this approximation of transforming the control points and coming up with a new patch.
Before we leave those algorithms, I've asked the grungy question of exactly how fast were they?
Exactly how fast were they? That's a question everybody always asks, but there's no real good answer. I mean, one of these things made a picture of a teapot in about 4 or 5 minutes. The Catmull algorithm that I implemented took more like 45. I never implemented Wooded's version of it, so I don't know how it compares with the other one, but it'll be in that neighborhood, I guess. Well, it'll take change.
It's just nice to know order of magnitudes at least.
Yeah, it's so much a function of what machine you're on, what language you use, the particular programming style you use,
How much memory?
and so forth, yeah.
You do these things often in Fortran, is that right?
Everything I do is in Fortran.
How do you do all this? You talk about linked lists and all that. How do you do
There are array indices.
So you have the gobs of this management that you do yourself in Fortran.
Well, I don't think you have to do any more or less than you do in any other language. Go ahead and change the tape, yeah. Pause for a minute while I change the tape. Which, the machinery for sending assignments from here to there, I think I've been putting them in that little wooden box, but I'm not sure. Yeah, okay. Okay, great. Sure. Okay, back in. Let's see, where were we? The next thing is the next level of algorithm here, which is Lane and Carpenter. And they do sort of a combination of Catmull patch splitting with polygon tiling, kind of in parallel. And they have two lists of things. Same as any other algorithm does. You can call it the active list and the potential list. The active list is what's visible on this, what intersects this current scan line, which is what's used for the X scan across that list. Potential list is kind of the Y sort list. Those are the things that are sorted in Y but haven't poked through the scan line yet. The things on this list, however, are patches. And the things on the active list are polygons. Rather than having them be both polygons or both patches, is what's happened in the other algorithm. And when you go down a particular scan line, you do the following thing. You update all the information for the active list as you normally do. That's incrementing all the X's and Z's from along the edges and the intensity information. Any polygons that drop below the current scan, or that the scan line drops below, you throw those away, remove them from the active list as in the standard algorithm. And then you take a look at the potential list. Now for each patch that's on that potential list, we want to do two things with it. If that patch is flat, and if it intersects the current scan line, we move it into the active list and turn it into a polygon. Now by flat, I mean a patch that's so close to being a polygon that you may as well title it as being a polygon. And by intersecting this current scan line, I mean that the maximum y, again, for like Bezier control points, you take a look at the maximum minimum y of all the 16 control points, and if that overlaps the current scan line, that means it's potentially visible. Now for something that's below the current scan line, we just leave it in the potential list. We haven't gotten to it yet. And so we're really only looking for things in the potential, list that have now decided to poke through the scan line when it goes down. If the thing pokes through the list, pokes through the scan line, but it's not flat, you split it into two pieces, or four pieces, and put those on the potential list. So what we're effectively doing here, as you go down the scan line, each time a patch pokes through, we split it into pieces and test each piece so that if it turns into what amounts to a polygon, we just turn it into a polygon and use it. If it's the piece that we split it into is now the part that's below the scan line, we stick that back on the potential list. We're not interested in it yet. And for things that still poke through the scan line but are not flat enough yet, you subdivide it again. Right? And so it's a kind of a scan line by scan line version of Catmull's algorithm. You whittle the patch down, and so your criterion now is not it's 1 pixel big. The criterion is it flat enough to be treated as just a regular polygon. And this is fairly straightforward. The potential list can kind of get cluttered with a lot of little patch fragments kind of clustered close to just below where the current scan line is. The patches that are way below the current scan line haven't even gotten looked at yet and split, so they're going to be still in their large, big state. But ones that poke through are going to get split into little fragments. So you've got this kind of collection of little fragments waiting just below each scan line as it goes down. But apparently the number of patches does not explode too rapidly here, so that you are in too much danger of running out of space. There is one problem with this thing, and that is holes. We have a patch like this, and when the scan line comes down here and it's not flat enough, you would divide it into 4 pieces. And let's say this piece is now flat, so it's going to be treated as a 4-sided polygon. Just connect the 4 corners together, tile it as a polygon. Now, when the thing gets down to this particular polygon here, just that 1/4 of it might not be flat enough. It might be a little bulgier, and so you have to split it twice, like that. And then those 4 pieces are flat enough. So you have these 4 polygons like that. Now look at the area right in here, which I'll make a magnified view of. This is the 2 corners of from the center out here like that. And for the upper polygon, since it's flat, it's going to be treated as a flat polygon, so it's going to be connected with a straight line edge. And the bottom polygon here, or the bottom patch rather, since it's been split, it's going to be connected into, here's what the real edge is, and so the split is going to connect a thing like that, and like that. And so this little triangular area in here might leave a hole in between these two things. And if you are so unlucky as to have the pixel fall into that hole, you wind up with a hole in the picture. Now, if you're doing anti-aliasing, your area sampling, sort of, you're expected to average together the whole polygon here in the region surrounding that pixel, and so the effect of one skinny little sliver through here as a whole is going to be much diminished. It might be sort of noticeable as some little grainy speckly pattern that kind of creeps around on the patch. But area sampling will get rid of a lot of these problems. There were some other techniques that they used to worry about that, but that started getting into the heuristic sort of game again, in that they kind of kept track of the fact that this thing was split different amounts on one side or the other and somehow glue this back together again or whatever in order to try to get rid of the holes. But this is a fairly good algorithm in that the splitting thing itself is nice because patch splitting is very easy mathematically, and it's sort of guaranteed to work in that no matter how many odd convolutions and bumps and wrinkles there are in the thing, patch splitting will always catch all of them. Whereas these iterative techniques that track along the derivatives and so forth can sometimes get confused at local minima or saddle points or places where the first 5 derivatives are all 0 but the 6th derivative is non-zero. The thing gets, has real bizarre effects like that. And so these are kind of the 3 main algorithms that are used for doing bicubic patches, and they each have their advantages and disadvantages. Yeah.
How do you define flat? Is that a heuristic?
Oh, how do you define flat? That's a good question. That again is a heuristic sort of thing, although there are various more or less reasonable ways of doing it. Let's take a look, start out with just at a curve. This is my cubic curve, and these 4 points are the Bézier control points of the mesh. Bézier control points are real nice geometrically for keeping track of what's going on the curve, in that for a curve that's only very slightly curved, the Bézier control points are very close to being on the curve itself. And so what you can do is take those 4 points and see if they're collinear. And the degree of non-collinearity is a degree of flatness of this curve. You can, for example, connect the 2 endpoints together with a straight line and then see how far the other 2 vary from the point. And you can say if the maximum variation of this as a ratio of the total length of this line is less than 0.01 or something like that, then this thing is flat. Now, extending this to patches is about the same thing in just 2 dimensions. You have 16 control points in a mesh. And if all those 16 points are coplanar, then the patch is flat in that sense. And again, you can kind of fit some sort of plane through them and see what the maximum distance of each of these points are from that plane to see how closely that is to coplanar. Now, just making these 16 points in the same plane is probably not good enough. What you want them to do is have kind of straight edges as well. It's possible to have the 16 control points do something like that, so that the patch itself looks like that. It's a planar patch, it's in the plane of the blackboard, for example, but the edges kind of pucker in a lot. And so what you really want to have is these 16 control points be kind of equally spaced apart in the plane that they define. These things get more and more elaborate to calculate, and you have to kind of do this each time you test a patch. One of the interesting things to do with all these algorithms is to do some real empirical experiments in how much time is spent doing these things. I mean, everybody sits down and philosophizes about n log n algorithms and n squared algorithms and does these theoretical analyses, and that's basically useless. What you're really interested in, how long it really takes, not how long theory will tell you it takes. And so you instrument your program. You start putting in, I think in Unix there's a profile program for measuring how much time it spends in which subroutine. One of the other tricks I did was have the code that I was did in assembler language, would each subroutine would stuff a particular value in the lights register on the front panel. And so you attach a light to each subroutine. Whichever light glows brightest, that's the offending subroutine, things of this nature. And you find out some interesting things about your program that way. For example, the implementation I did of Catmull's patch splitting algorithm, the place it spent most of its time was in a little subroutine finding the maximum and minimum of 16 numbers. That's the thing that determines if the thing is within a pixel or not. You've got, here's 16 control points for your patch. What are the maximum and minimum numbers so I can find the bounding box? That's where it spent almost all its time doing that. Because it has to do it so many times. Every time it's examining a patch, every time it's doing anything.
What algorithm were you using?
This is Catmull's patch splitting algorithm?
No, to find maximum minimum.
I don't know how many there are. You just say, take the first one and compare it with all the rest of them. These are not sorted in any way because they're the control points of a patch, which can have an implicit ordering to them. So I mean, maybe if there's a hardware array maximum routine or something that might help you out. Who knows? I think it's interesting experiments to do is to actually implement these things and test them out. All these papers about linear time algorithms and rah like that really doesn't make a whole lot of difference because what you're interested in is not so much the function of time as the coefficient that's in front of that. You can make any algorithm you like linear by putting an enormous coefficient in front of it, and you can just have it go through a loop doing nothing 200 million times for each patch. Now the time taken by this algorithm is linear in the number of patches, right? Up to 10 zillion patches, but so anyway. So that's basically it for patch drawing algorithms. There are a lot of things that you can do with bicubic patches, or in general parametric surfaces, which we'll get into probably next in terms of texture mapping, where you are taking other properties of the image being functions of the u and v parameter values besides just the geometric position on the points. That'll be for next time. What I want to do is to make a few random comments about anti-aliasing. I happened to sit up last night watching all the videotapes of previous lectures in the class, so I just watched Ed's lectures for the last 2 or 3 weeks worth on that. So I have just a few things to add to what he said. Basically, we both agree on the main idea is that you have to do something to get rid of the aliasing or the jaggies in the image. But in terms of what to do and the relative importance of these things, we have maybe slightly different views on. He is hot for using little box windows, area sampling. And if you have some sort of picture, then you just average the area surrounded by a pixel with an equally weighted window, and so forth. And that tends to be easy to implement, but it's not really quite accurate enough. Let me see, 10 minutes we can do this. Let me go through a mathematical definition of what I see aliasing as coming from. And what we're going to do is look at one-dimensional functions. So you can think of these as time signals, or just looking at one scan line at a time, something like that. And we're going to look at their Fourier transforms. Now, I presume most of you in here have at least some vague intuitive feel about what a Fourier transform is, or a harmonic series, something like that, Fourier series. And so I'm just going to write down what the Fourier transforms of various of these functions are, rather than prove anything about them. Here's a function which is a function of intensity. The x direction goes along like this, and it's some whatever. This is the ideal perfect image that we want to see. And it's kind of computed at infinite resolution. This is the mathematically perfect image. Now the Fourier transform of this thing will generally look something like this, where we're plotting here frequency along this direction and amount of, or strength of a component of that frequency like this. And it generally has some maximum near zero frequencies, and then There are higher and higher frequencies, but they're less and less important, less and less high contributions go in here, right? Now, all of the sampling business and all the filtering things can be thought of as watching what goes on in both of these domains sort of simultaneously when you do something to the picture. And so that's what we're going to do. Now, there's one basic punchline to Fourier transform theory that is we need to keep in mind here. And that is the relationship between multiplication and convolution. If you take two functions here and you multiply them together, that is, each point along here in x, you multiply the value of the function from the first function and the second function, just multiply them together, and this gives you a new function, right? What happens to the Fourier transform of that thing is that the two Fourier transforms are convolved with each other. Let me briefly mention what convolved means. Here's one function, here's another function. We're going to convolve these. This is another thing that you do to functions, and we're going to come up with the resultant function. Sometimes it's written with a star with a circle around it. At each point, in order to find out what the value of the convolution of these two is, you take this function here, and you plunk it down on top of this function, you multiply them together to get a product of these two functions, and you integrate the total area underneath that. That will give you a number. Then you plot that right there. Now you move over a little bit. You slide this over to here, you multiply the slid over function with the original function, multiply those, go point by point, integrate the area underneath that, and you get another number. So you plot that there. You slide this over a little bit more. You multiply this function by the other function, get the product of those two, integrate that whole area underneath that, giving you a number, and you plot that down here. So the new function is, the convolution of those two is the resultant of sliding this F2 back and forth along here, and at each point multiplying them together and integrating the area. So it's kind of a local area averaging process. That's convolution. Now, if we take the ideal function here, which is the precisely defined one, and we're going to display that on a screen which has pixels across it, we are not going to get the ideal function, we're just going to get samples of it, right? We're just going to be sampling the thing at various, presumably equally spaced intervals. And so that's like we're multiplying this original function by what's called a comb function. Here's a comb function. It's got a whole bunch of impulses here on unit height, and then it's zero in between. So if you multiply this comb times that function, we will get the sampled function. Right? What does this look like in frequency space? The Fourier transform of a comb function like this, abracadabra, is another comb function. The only trick here is that for really closely spaced combs here, the Fourier transform of that is really widely spaced combs. And for really widely spaced ones, the Fourier transform is really closely spaced ones. And so compact ones spread out and spread out ones compact. So this is the Fourier transform of the comb. Now, since we're multiplying this by this in the spatial domain, we have to convolve these things in the frequency domain. We convolve the frequency, the Fourier transform of this by this Fourier transform. Now, what's going to happen when you take this comb and slide it back and forth, integrating along the way? What you're going to wind up with are a bunch of copies of this overlapping copies all added together. like that. So this is the Fourier transform of the sampled signal. This is where the aliasing comes in. It's where these things overlap that you get into trouble. Because the next thing that you do is to display this thing. Now, once you've got all these numbers and you go to display them, you're not going to display infinitely bright spots exactly here and blank in between. You're really going to kind of interpolate intensities in between these things, right? Which is like convolving this thing with another little bump-shaped function. Here's the spot on the screen, right? And for the continuous functions you wind up in terms of intensity on the screen, you move the spot back and forth and you convolve it with this thing. And so it's going to sort of interpolate a smooth curve in between these things. For this point here, you're going to get the spot that just fits in like that, so you get this point. And as you slide the spot over like that, you get a weighted sum of these two until you have the spot centered here, at which point you get just this value. Then as you slide this thing over like that, you get a weighted sum of these two, so forth. So the spot is sort of an interpolation function. And so you get a smooth thing like that, smooth thing like that. Now, again, what happens to this in the frequency domain? Fourier transform of this spot is some other spot, or some other bump-shaped thing. And these are going to get multiplied together. So you multiply this with this, and you get back again this function. All these side lobes get multiplied by 0. Now what you want to do then is compare this that you came up with the one you started out with. This is the measure of how accurately you're doing it. Now in the ideal case with an ideal filter, you have, you come along like this, and in between here you've done a filtering operation to get rid of these high frequencies so they don't overlap anymore. That is, you have taken the Fourier transform of this thing, and you've taken all these things that are outside of this range, the ones that are going to overlap, and you set them to 0. Right? So that when you convolve it with a column filter, they all kind of butt end to end, but they don't overlap anymore. Like that, they're just glued exactly together, right? And then the particular spot shape that you really want to use here is the one that keeps the maximum information in this. We want to get back this stuff here and get rid of the outside edge. So we'd really like to have the Fourier transform of this spot be another little box here. Slices out just this stuff, throws this away, and so what we come up with finally is exactly the same original function with just the high frequency set back to 0. That means the Fourier transform of this box here tells us what the spot shape should be. Fourier transform of this straight-sided box like this is sine x over x. Well, now we're getting in trouble because it's kind of hard to get a spot on the screen that has negative intensities in some places and spreads out infinitely. Similarly, we have troubles here with setting the frequency things to 0 here, in that that again is impractical to do in real life in the frequency domain. We don't want to take Fourier transforms over the scan line of our picture when we're making it. So you do that by convolving the real genuine image with a Fourier transform of this thing, of this windowing function here. It, again, turns out to be sine x over x. So the ideal thing to do to your picture is to convolve a real image with the sine x over x in order to filter away the high frequencies. Now, one of the things that is generally done as an approximation is instead of using the sine x over x, you use various mathematical shapes which are similar in shape to this thing but easier to calculate with. The easiest one is another little box, which really isn't chopping this thing exactly like that. It's chopping it with sine x over x. So some of the higher frequencies that you could keep around are being scaled away by the fact this trails away slowly instead of abruptly dropping off. Some of the high frequencies that you need to get rid of actually stay around because of these extra lobes being out here, not being 0. And so the fact that these two are Fourier transforms of each other is sometimes a bit confusing, but this is only one of the possible functions. The next sort of function to use is a tent function, is a straight line approximation of this. Fourier transform of this is, again, it's a bump in the middle with a bunch of lobes in it. The lobes are smaller here, and this thing falls off to 0 a little bit more abruptly. As you get closer and closer approximations to this ideal filtering function, you get closer and closer to the ideal chop-off thing of the high frequencies. Now, Ed is very fond of using this thing here and saying that anti-aliasing is being done, but really you're only kind of improving things a lot, better than doing nothing, but you're really not doing it correctly. I saw an interesting demonstration of this applied to a test image at Ampex once, where you apply this box to the image with a particular test pattern that has a lot of high frequencies in it. You can see the high frequencies all go away. You say, well, that's kind of what you expect to get out of it. But later he applied this frequency filter to it. You can see much more crisp edges on there than you thought you could ever get away with on a TV set, and they all look correct. So the closer you get to this, the better the image is going to look, but the harder it is to write the program. Now, one of the specific cases where this box filter doesn't do a damn bit of good is drawing pictures of stars. Because here's the ideal picture of a star, right? And as this thing moves from one pixel to the next, if you were point sampling it, of course, it's totally useless. The star just never happens to sit exactly on the pixel. But if you use one of these box filters like that, as long as the star is near a particular pixel, that one lights up. And then when the star slowly moves over here, suddenly this one pops off and this one pops on. So the pixels go blink, blink, jerk, so you get this jerky effect on there. So just this box is not going to work quite as well. If you imagine a tent filter applied to this thing, here's the star, and here's the tent filter for the next pixel. What's going to happen is this pixel is going to be bright, and this one's going to be sort of half bright. And then as the star moves to the right, this one's going to go down, and that one's going to go up slowly until the star lines up with this pixel. And then this one is going to go, and that one's going to go up slowly. And so you get a little bit smoother effect in between. And so you can always come up with a bizarre case which you'll get nailed on for very simple approximations to this. Okay, that should do it for today.